Hello everyone, so in this video we're going to be starting a new series on the prime factorization, sort of just the factorization in general of both polynomials and numbers. So a factor of a number is usually a number that you can multiply together with another integer to get the number, like the number that is a factor of. So as you can see, 12 is 1 times 12, which is also 2 times 6, which is also 3 times 4. From this, you can get that 1, 2, 3, 4, 6, and 12 are all factors of 12. And multiples are sort of just reverse factors, where they're the products when you multiply two or more numbers, in which if you look, 1 times 12 is 12, 2 times 6 is also 12, 3 times 4 is also 12, so you can get that 12 is a multiple of 1, 2, 3, 4, 6, and 12. Now, any integer is always has itself and 1 as a factor, and it is always a multiple of 1 and itself. So to prime factorize a number, you basically express the number as a product of factors that are all prime, in which case if you look at 12, 12 is 2 times 6. But 6 is not prime, so you can factor 6 again down to 2 times 3, which means that 12 is equal to 2 times 2 times 3. And then you need to collapse the two 2's in 2 times 2 into a format in which we just use power of 2 to the second power to express this, so we get 2 squared times 3. Now here's an interesting and pretty useful prime factorization to remember. 1001 is prime factorized as 7 times 11 times 13. And yeah, it's good to remember if you ever have to use it. And prime numbers are basically numbers which have only 1 in itself as a factor. In which case, in this table, there's all the prime numbers that are less than 100. And if you look at 2, which is highlighted in this grid, it's the only even prime number. So yeah, that could be useful when trying to prime factor. Now there's a theorem called the fundamental theorem of arithmetic, which states that every positive integer has a unique prime factorization. So basically every integer has only one prime factorization, and each prime factorization only represents one integer. As you can see from this, no matter how you factorize prime factorize 36, you always end up with 2 squared times 3 squared. Also, if a number is a perfect square, each of the prime number factors will actually have an even exponent in its prime factorization. As shown here, if you look at a, with a as an integer and p and q both as primes, if a can be factored as p to the m times q to the n, then a squared is p to the m times q to the n squared, which by some rules of exponents, you can get that is the same as p to the 2m times q to the 2n. Now, since m and n are most likely going to have to be integers, 2m and 2n would definitely be even. And here's an example to look at. What is the largest prime factor of 189? Now, when factoring, you sort of just attempt to see if any of the prime numbers can divide this number. So if you look at it, you can't be divided by 2 since 9 is not divisible by 2. The number in its integer is not divisible by 2, but it can be divisible by 3 because 1 plus 8 plus 9 is divisible by 3. Therefore, we can divide it by 3 in this sort of just tree method below to get that 189 is 3 times 63. And then if you look at it, 3 is a prime, so we don't have to continue splitting it down in the tree. But 63 is not a prime, so we can continue splitting it. And by the same method that we turned 189 into 3 times 63, we can get that 63 is 3 times 21. And then again, 3 is a prime, so we don't have to split it down in the tree anymore. But 21 is not a prime, so we continue splitting with the same sort of method to turn it into 3 times 7. Now 3 and 7 are both prime, so you can just end this tree diagram here, and you can see that it equals 3 times 3 times 3 times 7, which is 3 to the third times 7. Now, out of 3 and 7, 7 is larger, so the largest prime factor is 7. Here's another example. If the product of 1080 and an integer is a a perfect square, what is the smallest value of a? Now, if you look at 180 and we do this with 1080, sorry, and we do the same thing, we can get that this thing starts off divisible by 2, so we can get it that it's 2 times 540. 2 is a prime number, so we can then split 540 into 2 times 270. 272 is again a prime number, but 270 is not. Continuing splitting into 2 times 135. 2 is a prime number, 135 isn't. You can split that into 3 times 45. 3 is a prime number, 45 isn't. And then you can turn it into 3 times 15. 3 is a prime number, 15 isn't. And then into 3 times 5, both of which are prime numbers. So you can get that 1080 is 2 times 2 times 2 times 3 times 3 times 3 times 5. In which case, 2 to the third times 3 to the third times 5. Now to make this and times a to be a perfect square, you're going to have the product, which is basically these three, this prime factorization times a's, the number a's prime factorization. You need to make all the prime factorization of the end product have all of the prime numbers powers be even. That would mean that 2 to the third, 3 to the third, and 5 are all, since 2 to the third, 5, 3 to the third, and 5 to the first all have odd powers right now. You're going to have to multiply it by a 2, a 3, and a 5 to turn them into even factors, basically 3 to 4, 3 to 4, and 1 to 2 power. So that would mean that a must equal 2 times 3 times 5, which would equal 30. Now this is the smallest a value because you can't sort of just divide, you can't take out any of these factors in the prime factorization, and adding anything else, any prime, because all primes are larger than 1, would make this larger. So 30 is the smallest. Now here's something for you guys to attempt. Now try to factorize 45, 88, and 126. Now pause the video now if you want to attempt this. Now I'm assuming that everyone paused the video and attempted these 3 questions. So here are the solutions to them. Now, thank you for listening, and next time we'll mostly be talking about how you can get the number of factors that a number has, as well as the sum of those factors. And that's it for this video. Bye.